Hello, my name is Nandipha Masondo. I am an MSc candidate at the University of the Witwatersrand in the School of Geosciences, being supervised by Professor Raymond Durheim. The project that we'll be speaking about today is the thermal spalling project. South Africa has had many years of experience in the mining industry, and this has led us being masters of rock breaking methods. The typical ones generally include the chemical methods, blasting, as well as excavation methods. But in this talk, we'll be referring to the thermal spalling rock breaking method. So thermal spalling is in essence an application that requires direct and rapid application of heat onto a rock's surface. This has been used in a number of different mines in order to mine thin reef gold. A successfully implemented one was in Nippon Dragon in Canada, and we have tried it ourselves in the country at an Anglo Gold Ashanti mine between 2014 and 2018. The principle behind thermal spalling is the application of direct heat onto the surface of the rock. This initiates flaws and propagates them to the point where we reach the second stage, where the faults coalesce and grow throughout the rock. Once the faulting has expanded, then a small chip is eventually detached from the sample itself, and this is the goal for thermal spalling. Our mandate in studying this mechanism was to master the rules so that we'd be able to break them. The concept has been proven. We know that it works in real mines, and the technology is available. This all then makes it necessary to see how exactly it would be applied in the context of our own reefs. From the Anglo Gold Ashanti trials, we know that it works in the gold reef. But what about the rest of them? South Africa has many different minerals, particularly the PGM reefs are of interest in the study. Through the study, we'll learn how the whole process works and what exactly affects it in the heating process as well as on the surface itself, on the rock surface itself. The first stage that we needed to go through was designing the lab equipment that would closely resemble the mining method used underground. This included using an oxyacetylene torch as our heat source and then mounting the core sample of the reef in which we're interested in onto the spalling rig. The torch is then placed on top of the sample on the other side of the spalling rig, so that the surface just touches the rock surface. The heat surface just touches the rock surface. The samples of interest in this study are the ones that we get most of our mineral wealth from. This is the Wits quartzite for gold, our Marinsky Reef pyroxenites, and our UG2 for our PGMs. For the Wits quartzite and all the rest of the samples, the main point of investigation is what's on the inside. How is the rock itself composed of? How is it fractured? How do the grain sizes and the shapes of the different types of minerals in the rock interact with each other? And this all affects the rock's strength of the entire rock and makes sure that it is spallable or not. In the mining context, you would be looking at working with rock sizes in the macro stages. But for this study, understanding what goes on inside the rock so that we could also scale it up to that point, we are focusing on the microcracks, as you can see on the images. This is a thin section microphotograph of the Witwatersrand quartzite. Here, as will be done and seen for the upcoming samples, we aim to characterize the mineralogy of the rock. We aim to see how altered it is, what kind of effects it might have on its own spallability. And this includes just characterizing the entire section and making sure that you understand what microfractures there are, how they might behave with each other and with the matrix itself. So just as an indication of how different each of these rocks actually look under thin section, the previous slide showed the Wits quartzite thin section. This shows us the UG2 section where we get our chromatite. The other sample, which is the Marinsky Reef pyroxenite, is also a very interesting, is also an ore body that we have always been interested in. So all these three rocks clearly have very, very different textures and very different fracture patterns. They aren't the same. So how would each of them react to being heated to the point of rapid fracture? Each of these samples were placed under a thermal load, a rapid and direct heat for the same amount of time at the same conditions. And some of them, as you can see here with the Wits quartzite, produce chips that fly all over the place. Now this is all related to how the heat itself interacts with the sample. This is a close-up of the small chips which are the goal of this project that have formed on the Wits quartzite. There we know it responds positively. When the exact same method is applied to a sample from the Bushveld complex, this here being the pyroxenite, it almost goes quiet. And you can see very clearly when you check the surface and how each of them reacted to the exact same conditions, and there was melting on the pyroxenite as opposed to that almost perfect spalling on the Wits quartzite, it becomes important to understand why this happens. Apart from the factor of the mineralogy of the rock as well as its texture, other factors greatly affect how it would spall. We've seen this through our experiments, that the saturation level affects how the material responds, the torch angle, how is the heat applied, the flame temperature, which is determined by the type of gas as well as the gas pressure that you choose to set it at, as well as any pre-treatment or in-situ conditions that the rock was exposed to. This all gives us a step in the right direction for understanding which aspects to further investigate. This work will include further microanalysis, fracture analysis, thermodynamics, fracture models to understand the processes and how all the components involved interact with each other and depend on each other, so that we can achieve the ultimate goal and apply the set recipe that we'll be getting from the project to underground mining. Thank you.